Okay, hello everyone. You should be able to hear me, and I hope you are able to enjoy the video stream in silence now. Give me a thumbs up if you can hear this, or if there are any issues, give me a question mark with number 5 or so. I guess if there are issues, no one's going to hear it, so I shouldn't expect to see any question marks except for one or two jokers among you, right? Um, so what we're going to be talking about today is 2 and 3-dimensional kinematics, continuing and finishing that up. The thing we were completing there was the aspects of relative motion. And then we're going to talk about forces. In particular, we're going to introduce Newton's first law towards the end of the class. So let's start with where we left off last time, which was this topic of relative motion. The main formula there, and of course you don't need to memorize formulas necessarily, but if you memorize formulas or you know which ones to use, then at least solving problems will go quicker. So the main formula there is that the velocity of, in this case, the example was the person with respect to the train, is the velocity of the person with respect to the Earth plus the velocity of the Earth with respect to the train. So it's moving from one reference frame that is moving with a velocity to another reference frame that is not moving. And of course, if we have the velocity that changes this way, then similarly the acceleration will change this way. However, we will be moving from reference frames to other reference frames, only between reference frames that are moving with constant velocity. So we're not going to be having an acceleration to the reference frame. So if I want to write this for those reference frames, I don't think I have a slide on that. Well, there's that one again. So I don't have a slide on that, so let me write that down. So relative motion. So for a velocity of a particle p in reference frame s prime, that will be the velocity of particle p in reference frame s plus the velocity of s in reference frame s prime. And then if we go to the acceleration, we get a ps prime is a ps plus a s prime, where this will be 0 for transformations between coordinate systems. I say coordinate systems, I should say reference frames, which is the same thing, of course. Reference frames in this course. So that will mean that Vs S prime is going to be constant. Or of course 0. But in any case, A S prime will be equal to 0. There will be no acceleration. And it also means, of course, no rotation. Because rotation, we now know from uniform circular motion, rotation actually corresponds to an acceleration, a centripetal acceleration. So we're going to stay in we're going to transform between coordinate systems and describe things like relative motion in coordinate systems only that move with a constant linear velocity with respect to each other. So we started looking at an example last time. There's the slide with the truck and the car that both arriving at an intersection. The velocity of the car with respect to the Earth, VCE, is 80 kilometers per hour in the let's call this the x direction, which is the east direction in this drawing here. And then the velocity of the truck with respect to the Earth is 70 kilometers per hour, and it's in the negative y direction if we pick our xy coordinate system along the east-north directions. So we can write this down, right, in components. Let's call this example car and truck intersection. So VCE is 80 kilometers per hour in the x direction, and VTE is minus 70 kilometers per hour in the y direction. So those are the vectors for the car and with respect to the Earth, and the truck with respect to the Earth. One of the things we can immediately do, by the way, is also now say that the velocity of the Earth in the truck's reference frame is 70 kilometers per hour in the y direction. So if I'm sitting in the truck and I see the Earth move by, the Earth will move by in the positive y direction. So it will look as if the Earth has a positive 70 kilometers per hour in the y direction velocity. So this is the, for those of you who have taken the train, this is essentially the station is leaving with respect to the train, right? You all have possibly had that experience when you're sitting in the train and it accelerates so slowly that you hardly notice it. So now we can, of course, calculate the velocity of the car with respect to the truck. So that will be VC Earth plus V Earth truck, which is why I, of course, introduced that here. So that will be 80 kilometers per hour in the x direction plus 70 kilometers per hour in the y direction. And then, of course, we can calculate the magnitude VCT. So that will be 80 kilometers per hour squared plus 70 kilometers per hour squared with a square root, just using the magnitude of this vector, right? So that is going to be this vector VCT, and so if I'm thinking from the point of view of the truck, which is the reference frame here, the car is coming at me with that vector and in that direction, and we can actually calculate this angle theta here, and theta will be the inverse tangent of VE over VET over VCT, so that will be tan minus 1 VET magnitude over VCT magnitude. And if you plug in the numbers, you'll find this is 41.2 degrees. And just a little bit about the terminology. So you'll see the book talk about degrees north of east in this case. So this is the direction towards the east. North is in that direction. So north of east is between east and north, starting at east towards north. So this is going to be called north of east. It's kind of the language that that the book uses for that. Okay. So I've told you last week that we were going to connect this with sailing. I don't know if there's any people who are sailors in the room. If you give me a raise your hand if you've been sailing on I don't know, Lake Winnipeg, Lake Manitoba or so here. Anyone? Nope, doesn't seem like. Oh yeah, there's someone. Okay, excellent. Yeah, that's quite a trip to Hecla and back. So then you know what a collision course looks like, right? Example, a collision course while sailing. So I hope you haven't had too much direct experience with collision courses. But one thing you'll know is that when people are, when we have one boat here, and there's another boat here, and this one is moving in that direction, and this one is moving in that direction. So this is the velocity 1 with respect to the Earth. This is velocity 2 with respect to the Earth. The way to tell that you're going to end up at the same point at the same time is if from boat 1, if you project this to the horizon, if you in other words look at where that boat appears on the horizon, if that point doesn't change, if a little bit later your boat is here and the other boat is here, and a little bit later your boat is here and the other boat is here, if that direction doesn't change and it's always pointing to the same point on the horizon, where hopefully you have a tree or another marker that you can look at, that will mean that you're on a collision course and you'll end up at the same point at the same time, which is of course not a good thing. If on the other hand that direction changes, let's say we remove these lines here, let's start drawing that over again. So if, let's say, we start off now in this situation, and a little bit later this boat is here, but this boat is a lot slower and is only here. So now the direction between these two has changed. So from the point of view of sailboat 1, sailboat 2 will appear at a different point with respect to the horizon. So now we can of course continue that. So another time interval later, boat 1 will be there, boat 2 will have moved a little bit and will be here, and again they will be at a different point on the horizon, and so the fact that this boat 2 is moving with respect to the horizon indicates that that there's not going to be a collision course. Now if we put this in terms of the reference frame of boat 1, so what's really happening in the first case is that the relative velocity of boat 2, v2, with respect to 1, which is the relative velocity of the second boat with respect to the first boat, is going to be points straight to boat 1. And that's of course the case when there's going to be a collision. So in case of collision, or in case of a collision course, the fact that this vector doesn't change direction means that it's going directly towards both 1 in that relative reference frame, and that of course is the thing you want to try to avoid when you're out on the water. Okay, another example where this will occur is problems like this, where we have an airplane that is flying at a certain speed with respect to the ground. This is called the ground speed. VPG is the velocity of the plane with respect to the ground. But there's some wind as well here, and the wind is such that the velocity of the air with respect to the ground is pointing in this direction. So for the plane to fly perfectly in the direction north, when there is wind that is coming at 45 degrees south of west, it means that the plane's speed with respect to the air, which is really the direction that the plane is heading, and the direction in which it is facing, that will be slightly different, because what will happen is we'll end up with the plane moving relative to the air in this direction, but at the point when, you could think of it this way, at the point when the plane gets here, the air has moved here, so that effectively the plane has flown with respect to the ground along the northern direction. So this is one example of this kind of problem. Another formulation of this kind of problem is using water currents. So let's do an example of that. Example of a swimmer crossing a river. I guess since I asked anyone whether they had been sailing, maybe I should ask, has anyone swum across a river here too? Maybe raise your hand when you've done that, when there was some current, and you've had to take into account the direction of the current to limit the distance that you wanted to swim. You know that if we have a river here, for example, I see many swimmers there as well. So if we have the velocity of the water with respect to the ground, and if the swimmer with respect to the ground wants to swim in this direction, then of course the swimmer will have to swim with respect to the water in a different direction. In which direction will the swimmer have to swim with respect to the water? And in other words, in which direction does the swimmer have to face to actually get a ground velocity that is completely perpendicular to the direction of the water current here? So think about the direction. I'm going to add some numbers here, by the way. So I'm going to take this. If this is 3 meters per second, and let's call this the x direction. And if I want this to be along the y direction, then we'll want to know what is the velocity of the swimmer with respect to the water. And I'll know two things. We'll assume that we know that this is 5 meters per second. So this is a pretty good swimmer. A swimmer who can swim 5 meters per second, well, yeah, this isn't the number that is picked for being physically relevant. This is a number that is picked for being mathematically easy. So the question is now, what is going to be the angle of the swimmer with respect to the y-axis? And then the other question will be, what will be the magnitude of the velocity the swimmer with respect to the ground? So I've only given here the fact that it is along the y-axis and along the y direction, but I haven't given the magnitude, so we will be asked to calculate that. So I see some of you are already quick at calculating that, and then I see a couple of people have given already the direction. So the direction in this case will be in this direction. I have to, as a swimmer, I used to be a swimmer myself, as a swimmer I have to swim slightly upstream so that along with the motion of the water with respect to the ground, I end up swimming straight across the river. And of course I've picked the directions and the angles now such that if we draw a little triangle here, this is V swimmer with respect to ground, this is V swimmer with respect to water, and this is V water with respect to ground. So those are our vectors. This is 3. I've told you that this is 5. So this will have to be 4 in our right angle triangle here. And this angle theta that we might ask, so if I express this as an angle, this would be west of north. So we can calculate that angle, and I actually didn't plug in the numbers, but I think Kevin puts in there that it's 53 degrees, which sounds about right. And so this will be 4 meters per second as a magnitude for crossing the angle. Yeah, you could also say, of course, that theta is 128 or 127 degrees if you give that angle with respect to the x-axis. So this would be equivalent to 127 degrees with respect to the x-axis, right, in the regular coordinate systems. Those are all different ways of expressing the same information. Okay. I see several have your hands up, but that's probably still from either swimming or from sailing. So okay, so now next time when you're swimming across the river, you should be able to make sure that you swim as little as possible in distance to end up exactly at the other side of the river by taking into account the proper currents. Good. So we're done with chapter 4, and we're done with essentially the first part of the course with this now. We've talked about kinematics, and then if you remember, I introduced kinematics as the study of motion without really thinking about why that motion happens. So, even just thinking back of this problem with the swimmer, I didn't care about how this swimmer is exactly propelling herself. The swimmer goes forward. There is some constant velocity. There's some constant velocity to the water, but there's no regards to what is exactly causing that velocity. Now, in the next chapter, we're going to be talking about dynamics. So, from kinematics, we're going to dynamics. And dynamics is the study of how forces cause motion. And I will say from the start that forces is the one thing, the one word, fortunately, in this course where the physics definition is pretty much exactly what you think of as a force. A force is, without being mathematical about it, is pushing or pulling on an object. So if you, I think there's a couple of slides here. Well, there's Newton. We'll come back to Newton. So if we think of someone who's standing on the ice and is perfectly free to slide around on the ice, again, we're ignoring things like resistance. So if there is a force, the force, if there's two people pushing this person, person one pushing in this direction, person two pushing in that direction, then that person will experience a force. Will experience two forces. In fact, since both of these forces have a direction and a magnitude, one person can push less hard than the other person. Forces will actually be they will be vectors, right? So they'll have a magnitude and a direction. So this is a vector quantity with a magnitude and a direction. So I do want to, I see some things in the chat there. Someone is mentioning twist. We're not gonna, twist is not a word, is not a physics word. It is also not something that we're going to talk about as all that separate from forces. Instead, what we're going to think of, if I want to make something, let's say, if I have a straight bar of something, let's call it a 2x4. If I want to make the 2x4 rotate, let's use a rotation. If I want to make the 2x4 rotate, I will have to exert a force in this direction on that side of the 2x4 and a force in that direction on the other side of the 2x4. So we're going to think about rotation later in the course as being caused by forces, and it's not going to be independent. There's not going to be an independent concept of twist or rotation, or the way you're probably thinking about this is torque. That is the specific terminology we're going to give to a specific configuration of different forces that causes direction to change. At this point, we're not going to talk about direction changes, because what we're going to be doing is essentially thinking of all of the forces as applying to a single point on the object. So I'm going to remove this here because I don't want anyone to be confused. I'm going to remove this circle here too. Hopefully, if I can actually select it. I'm going to remove that to not confuse you, because we're not going to talk about that until at least a couple of weeks from now, probably 6 weeks or so from now, if I remember correctly what the schedule says. So what we're going to be looking at a lot in the next weeks is so-called free body diagrams, or FBD. You'll see this referred to in the textbook. It will say, you know, draw FBD, or in the figures, in the captions, it will say FBD for the problem, I don't know, 5.7 or who knows what. So what is a free body diagram? It is a diagram. So it's a diagram, or a schematic representation of all external forces working on or acting on an object. I will underline schematic. That is different from artistic. So a free body diagram does not have to accurately represent in a photorealistic way how the situation looks like. It has to be a schematic representation. I'm going to underline all and external forces. So the thing that we won't want to include are internal forces. So, for example, if I were to go back to the the ice skating scenario here, if this person pushes against the back of the first person, well, then you might argue, well, obviously there's going to be some force from the skin onto the bones, and then there's going to be some force from the bones onto the bones in the bones in the back to the bones in the legs, and then there will be some force from the bones in the legs on the ice skate, and there will be some force from the ice skate, and finally on the ice. So most of those are all internal forces. We don't care about those internal forces in the person, but we care about the external forces that are acting on the outside of this person. And finally, and this goes with the schematic representation, we're going to represent this all as working at a single point. Acting, so it's a schematic representation of all external forces acting on an object as if they were applying on a single point. So in the case of this ice skating scenario, this is, there's the free body diagram. We've got two forces. F1 is in this direction, F2 is in that direction, and it is common to have the arrows pointing, and it is not just common, but it leads to the least amount of confusion if you do this, to have the arrows coming out of this point as if they're, you know, you might think of this more as pulling in this direction and pulling in that direction, but because this is a point anyway, that's equivalent to pushing F1 in this direction or pushing F2 in that direction. So we're going to have the forces appear as coming out of that point, and drawn with forces coming out of the point. I mean, maybe I should phrase this differently. With force vectors starting in the point. Okay. So the way to create these free body diagrams, as we do here, for example, is first treat the body that you want to describe the motion of due to these forces as a single point, and pick that point at the center of a coordinate system. Then draw the forces from the point outwards, and of course the next step will be determine the components in this coordinate system. So F1 will just have a component in the x direction, F2 will have a component in the y direction, and then finally, this will be the thing we're going to do typically, is calculate the total force or the net force or the resultant force. So total force or net force is the sum of all forces summed over I, right? So that's going to be something we're going to do a lot in the next weeks. We're going to apply that to these kind of scenarios where we have forces applying on a single on a person, and that causes this person to move, for example. We're going to look at that as forces for objects that are resting on a surface. So in this case, there will be multiple forces, and I can tell you right now that there's going to be a force that is going to be the weight that is trying to pull this object down, and there's going to be a force, a normal force N, that's a contact force that is pushing, that is the table or this horizontal surface pushing the box up. In this case, they're going to be in opposite directions, and their magnitudes will be such that the box remains at rest. And we'll talk about that in probably in 7 minutes. On an inclined plane, it becomes a little bit more difficult. Now we have the normal force, which is still normal to the plane. We have the weight that's still pointing vertically downwards. So there has to be, if this is to be at rest, there has to be another force that is slightly along the plane to make sure that these add up to 0. But we'll come back to that a lot. This indeed will require that we talk about friction. So let's talk about the different kinds of forces. There's essentially 3 types of forces, and I actually just introduced them here. I introduced a normal force, a weight, and some other forces. So let's start with a different type of force, which is a restoring force. If we have a spring or a rubber band or something, there's an equilibrium length when you're not pulling on the spring. This is going to be the length of that spring. If I now pull on the spring, I apply a force on that spring that is pulling outwards. What will happen is the spring will exert a force that is equal in magnitude, that is trying to restore the equilibrium situation in panel A here. That is going to be a type of force. This is the restoring force. So it's a force that tries to bring this system, this spring, but this will be true for many different systems, will try to bring it back to its equilibrium. If we were actually in an auditorium, I would be able to show you these kind of devices with springs that you can actually use to measure the magnitude of forces. The more you pull on this, the harder you have to pull on this, the more the slider goes out, and it shows you 1, 2, 3, 4, up to 10 Newton, for example. You might also have seen this as a way, as a scale to weigh heavy objects. You hang it from here. You hang this at a fixed point, and it will tell you what the mass is of the object. So that is restoring forces. These are very common. In particular, this kind of model of using a spring with a single restoring force that tries to bring everything back to the equilibrium is probably the most common model anywhere in physics. This occurs everywhere there is even anything that looks like an equilibrium. The next force could be these contact forces. So for example, here there's a contact force that the chair exerts on the person. So the chair in some sense pushes up against the person. The table pushes up against the arms of this person. The floor pushes up against the feet of this person. So those are contact forces. They always point in the direction normal to the surface that is providing the contact force. And then finally, there's field forces. Field forces are forces that are distributed over an entire volume, such as the weight. This person's weight is distributed over the entire person's body, right? Nevertheless, in our free body diagrams, we can think of this weight acting only on a single point. And you can think of that as the center of mass of this person. But it doesn't necessarily even matter exactly where we think that force applies, at least not until we start talking indeed about torque. So then one last thing about forces before we start talking about the first law of motion is sort of the typical units for forces and the magnitude of forces. So units of force are the Newton, or N, and this is where I should now go back and give Sir Isaac his moment in the spotlight here. So he came up with a lot of the stuff here, including the calculus. So you know who to blame for calculus as well. So let's see. I was on here, right? Yeah. Okay. So units of force are the Newton, and 1 Newton is about the force required to lift. I'm gonna put this, in quotes, to lift 1 average apple. Of course, Newton is famous for his apples, so I like to make that similar to the weight of an apple. So if you take a moderately sized apple, the force it requires to lift that apple is 1 Newton. So that sort of gives you an idea. Something that is going to require a 10 Newton force, you probably are still fine doing that. 100 Newtons, then we're starting to get into somewhat physical exertion. And 1,000 Newtons, I don't think anyone here necessarily would be able to exert a force of 1,000 Newtons. So that should give you an idea. Also, on the other direction, of course, in the other direction, if we're talking about micronewtons, those are going to be tiny forces, not just because they have a micro in front of it, but because they're actually small forces. Yeah, so if you, I am not responsible for anyone getting crushed if you try to do something with that 1,000 Newtons to prove me wrong. That's on you. Okay, so one last thing, and that is Newton's first law. I kind of probably shouldn't cover this in the last minute of class, but it is a fairly typical. It is a fairly well-known law, right? So Newton's first law says that any object that sorry, I have to think of how it is formulated in the book, but any object where there is no force applied upon will remain at rest or in constant motion, and it will only change its motion, its state of motion, from rest to being in motion, or from being at one velocity to being in another velocity, if there is a force applied. So for example here, I'm glad they came up with a Canadian example in this book that ultimately comes from the US. So the puck is at rest until there is a force applied to the puck, and of course the force here is the stick hitting the puck. At that time, the puck starts moving, as soon as the hockey stick stops touching the puck, the force disappears, and the puck will now keep moving at that same velocity. The only force that is applying on the puck is, of course, a little bit of friction. Well, the force that will change the direction, change the motion of the puck will be the friction of the ice, which can be small, but ultimately will, of course, slow down the puck. So we'll come back to Newton's first law in the next week, and of course we've got some other laws that will follow as well. Okay, that's it for today. So have a good weekend, and see you all on Monday.